So now, what we are going to do is, this is the layout we are given, and we are asked as consultants to design this system. We're asked to design this layout. So let's assume this is a layout in Abuja, somewhere in Buhari. It could be, now this is small, but in the real world, it could be bigger than this. It could be bigger than this. It is for the purpose of this training, you have to keep it simple and stupid. But it could be a district, it could be a region, it could be an estate, it could be a town also. But then if it's a town, I think it has to instead of 100 houses we have here, you're having like 1,000 houses. Now, when you are drawing your network, you are supposed to come up with something like this, skeletally. So these two and these two, they are just the same thing. But what you have done is to bring up this so that you can now use this as a distribution network to now do analysis. And I also said that you also have to come up with something like this in Excel. Okay.
Sorry, we only can see your whiteboard. We can't see what you show.
Oh, okay. Thank you. So this is what we're going to design. We're going to design this. This is the layout. You come up with this and these are the same, only that we've used the right of way to draw the pipe network. So the pipe network will look like this. Then your calculation sheets should look like this. You have to, this is what you need to do. This is how you must proceed, gentlemen and lady. You have to proceed this way. Okay, so here you list the sections, you list their length and then their elevation. Because I said the first parameter you need is a map and topography. So naturally, your surveyor should go to the site and take spot height, take the elevations, and you have them. And then at every point, you know the point A to point B, point C to point D, and so on and so forth. So that's what we have now. So out of the 4 parameters we are looking for, we already have 2. Out of the 4 parameters. So the node parameters now are the elevation of each point, which you get from your surveyor or from your survey data. You need a survey data, definitely. Number 2 is the demand. And I said this demand can also be called the flow. The flow, it can also be called the discharge. I think the discharge will basically come when you are doing something like stormwater or runoff. You use the word discharge, but they mean the same thing. In water reticulation, you call it demand, or you call it the flow of water at that point. They mean the same thing, and all of them are simply represented by Q. And of course, we know the formula for Q. Q means the area of the pipe multiplied by the velocity. In urban drainage, that area becomes the catchment area. And then your velocity becomes your precipitation. So let me just help us, even though that's not the course we're doing so. In stormwater design, A becomes your catchment area, becomes your catchment. And your V becomes your precipitation. V becomes, we call it I in that case. And it becomes your what? Your rainfall or your rainfall intensity. This is what you use, your rainfall or your rainfall intensity. So please, in this course, I want us to take note of this. Grab this, write it down somewhere, notice that somewhere. For you to do any water reticulation system, you need 4 parameters. Those parameters are pipe parameters and node parameters. When you talk about pipe parameters, you're talking about the length and the diameter. When you talk about node parameters, we're talking about the elevation and the demand. The demand at that point. So now, let's go back to this place and finish up what we did yesterday. Okay. So here now, I've been given this and I've come up with this. So let's calculate what is the flow. Okay, let me talk about the 4 parameters. For the pipe parameters, the length of the pipe will be given to you. If it's not given to you, you read it off from the diagram. You read it off from your chart or from your AutoCAD file. Or your surveyor, once your surveyor takes the spot height, all you need to do is to connect, use AutoCAD and connect the points. And then you can use inquiry tool in AutoCAD or your measuring tool, and then you read off the length of the pipe. The diameter of the pipe is what you don't know. But you cannot get the diameter of the pipe if you don't have the discharge. Then the elevation or at each point, your surveyor have done that, he has gotten it. So we have two parameters, we have two knowns, and we're looking for two unknowns. So the two unknowns now is the discharge and the diameter. Once you get the discharge, you use your nomograph, which is the chart we have, and then you get your diameter. Then when you get your diameter, your design is finished. Because the whole thing about pipe sizing, about water reticulation, is for you to be able to capture the appropriate size of pipe that will conveniently, efficiently, and effectively convey the water as needed. How many of you have lived in a house where the plumber uses half-inch pipe? That when you turn your tap in your kitchen, the one in your bedroom will not run. I don't know how many of us have done it. I don't know how many of us have, during those days in your universities, in the morning rush hour, suddenly the water will not be running again. Or the running will be running small. Once hostel A ons their tap, hostel B ons their tap, hostel C will not have water. It's a common thing. And the reason is wrong pipe sizing. And of course, basically it's wrong pipe sizing because if you use a big pipe, an adequate pipe, no matter what, there will be enough discharge in the pipe to take care of all the riparian points, all the contingent points. So in this case now, we are going to determine the discharge at point 12, and that discharge at point 12 is now for all the houses. These houses, no, and you can see it. All these houses connected to point 12. So for now, let's assume there are 10 houses. Yeah, they're not up to 10, but let's assume 10. Yeah, for ease of construction, for ease of calculation. Then remember yesterday we talked about, we did a calculation for one house. Let me just rephrase it again for those who remember. Remember we said for a typical 3-bedroom, let's assume that each of those dots represent 3-bedroom. We say for a typical 3-bedroom, we expect to have 10 persons, 10 C, which is 10 per capita. Okay, and we say we're assuming each person, per person, the standard, the specific water demand, we say let's assume 100 liters per capita per day. In other words, each person should not use more than 100 liters per person. And we say we have our peak factor to be, for ease of calculation, we say let's use 2.0. It's between 1.3 to 2.3. In other words, 230% or 200%. Should be 40% more. Your water reticulation should be, you should increase your whatever value you have by 30% to 200%. So there are some tests that will tell you something like that. Okay, so now we now say therefore the water demanded for 10 persons for each house is now 10 times 100 times let's use 2. The range is 1.3 to 2.3. Let's use 2 so that it will be easy for us to calculate. And the value is about 2,000 liters per day, no more. Then we say if you now convert this to a unit that we can use with our charts, which is you're converting it to liters per second, and that means converting it to liters per second will give us will now be 2,000 divided by 24 times 60 times 60, which is just 86400. And at the end of the day, you're going to get 0.023 liters per second. So in front of every house, if you use your pump and you measure the flow of water in front of your 2-bedroom apartment that is expected to contain 10 persons. Remember, it could be a duplex that can contain 10 persons. It could be a 2-story building that can contain 10 persons. It can increase to 20 persons. But it's an assumption. It's an assumption. You must make reasonable assumption as a consultant. So this is what it means. We now say, based on this, if there are now 100 houses what you simply do is now you multiply 100 by 0.023, which is the value for one house. Okay, whether there are 1 million houses, as far as you've gotten the value for one house, just multiply. So in our own case here now, we have about 10 houses. 10 houses connected to node 12. Therefore, pipe 9 to 12, which is referenced as node 12. I want you to understand the logic. Pipe 9 to 12, or section 9 to 12, or street 9 to 12. I've used 3 words interchangeably. They mean the same thing. I've used 3 words interchangeably. They mean the same thing. They mean the same thing. Either I say section 9 to 12, or I say point 9 to 12, or I say street 9 to 12, or pipe 9 to 12. It means the same thing, basically. So, point 9 to 12 now have 10 houses connected to it, and therefore we simply say hold on, from where we stopped yesterday. So section 9 to 12, which means I'm referring to node 12. Okay, 10 houses multiplied by 0.023. That will give me 0.23. Okay, so I need to have somewhere I should also be writing this. So node 12 now is equal to 0.23 liter per second. Yeah. Yeah. So now I now go to node, as I said yesterday, you cannot go to node 9, rather you have to go to node 10. And I said this dotted line means looping, it's just looping. So ignore it. This dotted line means looping. It means you can design this network as either as a loop system or as a branch system. If you remove all the dotted lines, it becomes a branch system. If you include those dotted lines, it means you are looping. Looping has advantage. Branch network has advantage also. In a short term, if you loop, why you loop is that if there is water failure in one area, like for instance, if there is failure coming from node 9, for instance, then water can flow from node 7. Or if there's a maintenance, midway 9 and 10, okay, if there's a maintenance midway 9 and 10, you know, the water will not flow to node 10. But because I have looped, or because I have designed the network as a loop system, because I have looped it, then water can easily come from node 5, 4, 5, 10 to 10. But the problem is that in loop systems are very difficult to design. They are very difficult to design, but there's a way to design it. The way to design them is to make use of dummies. You make use of dummies because that's where you start applying things like Hardy-Cross method. I mean, very difficult. You have to start to do interpolation. You start to do iteration because what you're trying to do now is to find the best value. Because it's like in project management when you're talking about critical paths. If you remember critical paths, you know, you have to start looking at which part is the easiest part or the easiest flow path. But save yourself that energy for now. Let's do a branch. Let's do a branch system. So for node 10 now, how many houses are connected to node 10? 1, 2, 3, 4. In real life, if you look at this one doesn't look like a 3-bedroom bungalow. This might be a hotel or a school. So the value will not be 0.023. So I have to go back and say how many rooms are in that hotel or how many rooms are in that hospital. And then what is the value from my table, from my standard? What does the standard says about the hospital? A hospital is about 200 liters per person per day, but the residential area is 100 liters. So you see, I have to upscale. Okay, just like when you go to all these places that looks unconventional, that looks, you know, that a little bit different, you must now investigate what kind of buildings are there. If it's a university, if it's a hostel, then you have to increase values. And those values are not increased arbitrarily, but they have to, that's where you have standards. You have your reference code and standards, which you use to say what is the reference code for a hotel, what is the reference code for a tannery, for a brewing industry, for a pure water industry. Of course, pure water industry is very easy. What is their capacity? What's the capacity of the machine? What is their output per day? That will just give you the amount of water you have to supply for them. Of course, you have to be in the planning anyway. So now let's say another 10 houses. Okay, so if you have another 10 houses, that means we also have for node 9 to 10. Okay, that means for node 9 to 10 now, we have another 10 houses. So therefore, we come down here. So here we say section, let me write it this way, section 9 to 10. Another 10 houses. Therefore, that will be 10. 10 houses here. 10 times 0.023. 0.023 means the discharge for one house. We've already factored in the safety factor, the number of persons in the house, and the specific water demand per person. So what we just need is what is the specific discharge going to one house. And we've established it since yesterday that value is 0.023. So this gives us another 0.23. So I can come here again and say the value for node 10 is equal to 0.23 liters per seconds again. With this value now, I can now go and now calculate for node 9, because node 9 is the one delivering to node 12 and 10. Okay, good. Look at node 10. Look at node 9. Now, the only thing is that, is there any base demand? Remember what I taught us yesterday. Is there any base demand for node 9? Is there any house that is contingent on node 9? I will just add it to the value of node 10 and value of node 12. So let's go back to drawing and see. If you look at node 9 is here. I can tell you, based on this 10 that I put here, there is no house on node 9. Why? Because this 5 and this 5, I've included it for 10. Then this one, 5 here, and this 5 here, I've included it for node 12. So I can correctly tell you that the base demand for node 9 is 0. Okay? The base demand for node 9 is now 0, but it is the pipe that's passing through the house, like I use a layman's language, it's already discharging to node 10 and to node 12. So the total demand in node 9 is not 0. But the base demand in node 9 can be 0. Yes, it's possible. It's possible. It's possible that there's an uncompleted building that is not taking water, but there's a pipeline that's passing through the uncompleted building going to 2 other houses that have people occupying them. So if I now tell you what is the base demand of that uncompleted building, it's 0. Nobody's living there. But what is the total demand flowing along him? It is now the demand of those in downstream. So now what we have here now? So we now say here now, we find out that we're on section 8 to 9 now. Am I right? Yes. Yes, 8 to 9. Okay. In other words, we are referencing node 9. Remember? So I need to take this thing out. Good. So now, good. So section 8 to 9. We are assuming it is 0. Therefore, section 8 to 9 also means node 9. The pipe is pipe 8 to 9, but the node is node 9. So node 9 now, the value for node 9 becomes, or let me put it, okay, node 9 becomes 0 plus, what is the value for node 12? 0.23 plus, what is value for node 10? Another 0.23. That will give you 0.46. Therefore, I can go here and say that node, this one is node 10. This one is node 9. Node 9 is now, of course, 0.46. You can see how I arrive at it. At least you can be writing, jotting down some things. Are we together? Yesterday, remember, we did some other notes. I think I should have been snapping all these things and be keeping them, but it's okay. Let's continue. So, okay, sorry. So now, with this now, we have node. Yesterday, I remember we got, can someone recall me what we got in node 7? I think we got 1 point, we got here 1.15. We got here 1.18. So here, I think we got about, okay, 1.22. Yeah, node 7 already, we got 1.22 yesterday. And how did we get node 7? Node 7 is the addition of node 11 plus node 6 plus its own base demand. So here we got 0.18. Here we got 1.15 or 1.15, yeah. Then here we got another 0. Okay, here we got 0.23. Here we got 0.18. By the time we added them together, we got about 1.22. And of course, this place is also what we got here, which is 0.81, what we got at node 13, plus 0.46 that we got at node 6. That was what gave us the total flow at node 6. Please take note of that. Take note of that. So now we have node 9 and we have node 7. So node 8 is now going to be node 9 plus node 7 plus its own base demand. If you look at this diagram, you see that there's no house between node 4 and 8. This is node 4 here. Node 4 is here and node 8 here. So if you look, there's no houses. This other house you're looking here is along this street. So you see that the base demand in node 8 is also 0, but the base demand in node 7 is 1.2, and the base demand in node 9 is about 0.46. So if you add those one together, you'll be getting about 1.7. Yes. So here we say that node 8, or let me start from here. We are talking about section 4 to 8 now, and the reference node is node 8. And we say that node 8 now is equal to 0 plus the value for node 7, which is 1.22 from yesterday, plus the value for node 9, which is 0.46. Please, if I need to recall how we got node 7, I won't mind. I can refresh it again. How we got it. If you have question on that, please ask me. Sorry, there's a mistake somewhere. So 1.22 plus 0.46 equals 1.68. Are we together? 1.68. Are we there? So 1.68 liters per second. So that's the value. 1.68. Okay. So here we can now go here. Node 8. is equal to 1.68. So you can see the value is gradually coming up. The value is gradually, is coming up gradually. So that goes to tell you that as the discharge is increasing, that is how the pipe size is increasing. So if you now leave this place and you now go to the next one, which is node 5 and node 3, before you get node 4, you must have a value for node 5 and node 8. So we've gotten node 8. So let us get the value for node 5. So what do you have in node 5? How many houses along node 5? Here is node 5. So we say 1, 2, 3, 4, 5, 6. 6. I'll count this one as 3 because it's like a massive house. So 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It has 15 houses. I can assume that there's also one unbuilt house here and making it 17. It's just your own discretion as a designer. So let me just summarize it as 20 houses for ease of calculation. Let's say there are 20 houses. I hope you won't be confused as to how we got 20. So let's say 20, okay, let's leave it as 16 houses. So 16 houses now, no, let's still go ahead with 20 houses. So 20 houses now, it means that value will just be 20 times 0.023, which is going to be 0.46. Yeah. Good. So here we say section 4 to 5. And the reference node is node 5. Okay? The reference node, section 4 to 5. The reference node is node 5. The reference node is node 5. And the reference node is node 5. So that means we now say the value is 20 times the value for one house, 2, 3. Which will now give you 0.46. So we are now on node 5. So node 5 is 0.46. 0.46, that is 4 to 5, means 0.46. So then we also do 4 to 3. So here we said we got to node, what do you call it again? Node 5 is 0.46. Okay. Then the next node we're going to get now will be node 3. We don't know what it is. So how do you go about node 3 now? How do you go about node 3 now? Node 3 is all the houses lying along this area. And how many houses are there? Oh, they are massive. 1, 2, 3, 4, 5, 6, 7, 8. Let's assume this one to be 4, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And a free space here, 20. So another 20 houses. Are you with me? I'm assuming 20 houses. But I can also not say 20 houses. I can say there are 10 houses, one shopping complex, one hotel, one garage, one this. That means for each of those different houses, different user, I will now have to calculate their water demand differently. That means at the end of the day, I will not have a homogeneous one value for across board, but at the same time, the value will be representative of what they actually is, what they actually are. In other words, if it's a bakery, if it's a hotel, if it's a hospital, if it is a mechanic, if it is a spa, if it's a swimming pool, all I want is for you to just generate the demand, the water demand, and then to add it up and to get the final discharge, which you now use for your pipe sizing. So in this case now, we have another 20 houses. Okay, we have another 20 houses. And therefore, it means we are talking about section section 4 to 3. And it's about 20 houses multiply by 0.23. And that will give you 0.46 again. And that will be the value for node 3. So we'll come here, say 0.46 again, liters per second. So the next thing now we now to do is the last node, which is node, not really the last node. The last node is the storage tank. So that will be node 4. Now, before we do node 4, we'll ask ourselves, are there houses connected to node 4 between 1 and 4? Do we have any houses there? So we'll go back to our drawing. Yes, there are houses. There are about 1, 2, 3, 4, 5. And in our characteristics way, we'll say, well, there are also meant to be houses here, but they are unbuilt. That is about talking about the future that I discussed yesterday. So let's assume there are another 10 houses again. There are another 5 houses on the opposite direction, making 10 houses. So that means the base demand for node 4 is already 10 houses. Then you now add it to the one from node 5. That means node 4 now has 10 houses as base demand, and then 20 houses as 4 to 5 at node 5, and 40 houses, sorry, not 20 houses at node from 4 to 3. So that means here I can go back. Hold on. I'm looking for my whiteboard. Okay, here it comes. So here we're talking about section 1 to 4, section 1 to 4, and we're talking about node 4. And we'll say that node means it's going to be 3 plus 5 plus base demand for 4. And that gives us what? What's the value for node 3? Node 3 is 0.46. What's the value for node 5? And that's 0.46 plus what's the value for the base demand for node 4? That's 0.2023. 0.23, sorry. There are 10 houses that are base demand that are contingent on him. So if you add up this thing, let me add it up. Okay. So that will be 0.69, if I'm not mistaken. 0. No, it's not possible. No, that's not possible. Sorry. Something is missing.
1.15.
Even at that, wait, let's go back. Let's go back. Oh, we didn't add number 8. We made a mistake now. No, number 8 is also part of it. So it's going to be base demand for node 4 plus node 5 plus 3, then plus node 8. Are you with me?
Yes, we are with you.
Good. So that would be, so the first value should be, what is the value again for node 8? 1.68. So the whole value now would be, what did you say? The other one is what? 1.15?
Yes, it will be 2.83 now.
2. Thank you. 2.83. Wonderful. I'm glad somebody's following. $2.83. 2.83. You know, have you seen what is happening? So if I quickly want to see the pipe size of this now, what I'll just do is I'll just go to my monograph. Okay, let me use the value, the assumption we made yesterday, which is at 0.1%, which is 1 per mil. Okay, so I'll just go me, I'll say 2 point what again? 2 point something, let's say 2.5. I'll just go here and I'll read it off. It will end somewhere here. And somewhere here is about 125. So you see, the maximum pipe size in this network is about 125 mm. Okay, well, somebody will say we've not gotten to the end yet, but it's good because what is remaining now is not really much. But I just want to give you an idea what next to expect. So now we only have node 1 remaining. And after node 1, I don't think there are houses here. There are no base demand again. So the only thing we have here is just this one, this node 2. So let's just assume, okay, 5 houses, for instance. So if you look at 5 houses, it's going to be half of what we've been getting for 10 houses, definitely. So here now, one can say, what section are we talking about now? Already, let's say section, let's just put the value there. Section, okay, section 1 to 2, yeah, is 5 times 0.03, which is equal to, what's the value? 5 times 0.023.
0.0.
Which is 0.12. Okay, so it means that node 4 is 2.83. And node 1 or node 2 is equal to 0. Node 2 is 0.12. Therefore, node 1, we all know what node 1 will be. Node 1 will just be 0.12 plus 2.83. What would that be? $2.95. Is it understood? Now, with these values now, what we now need to do is now we have established those four values. What we now need to do, sorry, we've not established, is to now go to our charts and start designing all these sections. You know, node 12, for instance, node 9 means section 9 to 8, 8 to 9, sorry. Section node 8 means section 4 to 8, and so on and so forth. So you have to now put in those values. And then use it to go and design your chart. So let's start with pipe 1, pipe ST to 1, which is the first pipe, the main pipe, the primary pipe. That's about 2.9. So that 2.9 is almost 3. Let's assume that the slope between, I don't want us to go to the question. If not, let's assume a slope of 0.1%, which is 1. So what I now do here is I'll come to 3. I'll come to 3. This is my 3. I'll read it off and then hit it against 1. Against 1 is perfectly in between 2 pipes. And those pipes are 0.12 and 100. So from what I said yesterday, if you get 2 values, you use the bigger one. So this is my 3 and this is my 1. So it's falling between 2 and it's falling almost on this line of 0.3. So the velocity is okay and the pipe size is 125 mm. I've designed it. That is your design. So the next thing you now need to do is that when you design all of them, you now go to your AutoCAD file, your detail, and then you start putting in the diameter of the pipe. You know, I want to give an example. If you want to detail, okay, I'm using it here already. If, okay, there's this one here. If you want to detail the pipe network, let's assume this is your pipe network. If you want to detail it, you come here, you write, don't know how to write it, but you come here, you write the diameter of the pipe. This is a symbol for diameter. You say equal to, or you might not even put equal to, you say 100 mm. You also put the length. Let's say 500 meters. The next thing, that's not all. Here, you say the elevation is about, let's say 260. And here elevation is about 262. As if you put the elevation, you also put some people put M, O, S, L, which is meters above sea level. Then that's not all though. Sometimes you can also put the invert level. You can also write the invert level. No, the slope. Yeah, I'm not remember the slope. You put the slope. So this is how to detail a water reticulation drawing. You can say 0.1. 0.1 is the slope. We know that in our chart it means 1. It represents 1 by 10. So these pipes also you also model, you also size it. So this is, I know some of them must have seen where they detail a pipe. So this is how to detail the pipe. So that is how to. So at the end of the day, you design. So I've designed for this one now. I've gotten 1.25. So the pipe size for this node 1 now is giving me 125 mm pipe. If I am thinking, well, I will know that node 4 will also be the same thing. Is it because I'm So no, from experience, you could see what it is. Then 0.46, I'll go to my chart and go to 0.46. Now there's no 0.46, the minimum you have here is 1. So it means that this chart, limitation of this chart is a discharge of 1 liters per second. Anything less than that, you can't use this chart. But the code also says that if you have something less than 1, you can assume the value for 1, only that the size will be too big, yes. But then the discharge of the flow is also too small. And that is why it's only in services pipe that you see all those kinds of small discharge. These big pipes that run along our streets, they are usually main pipe. They are in the range of 1 liters, 2 liters. Some can even get up to 20 liters per second. So, okay, someone have a question. So please, at this point, I want you to ask me a question. If not, I want you to bring up this chart and try to, in the next few minutes, I want you to try to calculate the demand and their pipe sizes. In this case, I want you to assume there are 50 occupants in each house. So here is an assignment. I just want, if you just do 1 or 2, I will just be impressed. I'll know, yes, you know what I'm doing. I want you to assume there are 50 persons in each house. We assume 10. Now I want you to assume there are 50 persons in each house. I want you to design few of the nodes, not all. Just let's say design like 13, 12, 13, 6, 11, 7, and then 10, 9, 12. If you get to 8, I think I'm okay. Let me just see. I want to see how far we are following. So I want you to do the demand. So the pipe length, the slope of the pipe remains 0.1%. The roughness, the nomograph to use, or the roughness factor of the pipe, I'm using MPVC pipe, which is very smooth. So the roughness factor is 0.1. So you know the chart to use. Then I want you to calculate for me, what is the demand at node 4 starting? What is demand at node 6? What is demand at node 7? What is demand at node 11? For each houses has 50 occupants. Your time starts now. Please, can I have a question? Somebody say, can't see the chart. The chart. Okay, I didn't share it well. Okay, somebody say, can't see the chart. Sunday, you say you can't see the chart, but you'll see it now. Are we together? Hello?
Hello? Yeah, I can see it now, but when you were explaining, when you wanted to do the sizing of that pipe, I couldn't see it there.
Again. Okay, this is 3. That's the biggest pipe, the main. This is my 3. My 3, and I'm using a slope of 0.1, which in my own charts, I'm going to use 1. So this is 3. So I'll read 3, and I'll get it to somewhere here in between. Look at it. Look at where it falls. And that means it's between these two diameters, this diameter and this diameter. This diameter is diameter 100. This diameter is diameter 125. So I'll use the bigger one, which is 125. For those of them that are below 1, I'll use the value for 1. So assuming I'm using the value for 1 now, it means I'm using a chart of 80. That means my minimum pipe size is 80 in the whole network. Because if you look at 1, I know everybody's watching me. If you look at 1 here, if you read 1 against 1%, 1 per mil, which is 0.1%, I'm getting this chart. So if you look at this chart is diameter 80, which is about 75 mm. From my experience as a water resource person, if you are doing water reticulation, it's as far as it's infrastructure design, let your minimum size be 75 mm. Let your minimum size be which is 80 mm. 80 mm is because of maybe British standard and German standard, because in our market we don't have 80 mm, but we have 75 mm. I don't know if I'm right. I know that you can't see 80 mm in the market, but that is what it is. So from experience, anything outside, anything on street, anything infrastructure, anything district design, the minimum pipe length, pipe diameter, sorry, should be 75 mm. So please, I want us to lay our hands on this thing in few minutes. In let's say 20 minutes. Are we together? Hello? Are we together? Please, let's. Yeah, I can hear you. Please go ahead.
Can you share the link where those materials are so we can go from here?
Hello, I didn't hear you. Are you talking? Are you speaking? Hello?
Yeah, can you hear me?
Hello? Assume 50-50. Safety factor is still 2. Number of occupants per building is 50. I know I want 50. I want something higher. And then what again? The water demand per person is still 100. The same parameter we use in our design, use the same parameter. But the only thing is that the land use says high density, meaning there are 50 persons per house. That means you must build at least four-story building per plot in that area. That's just what it means. So can we start now? I can see somebody working. That's Engineer Ilo. I can't hear you. You are muted. Okay. 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 The lecture material. Let me share it again. The lecture material. Okay. Share. Okay. Please see if you can open it. I'll share the material again. I'll share the material again. So we have like 20 minutes. Also, it's also a kind of break for us. 20 minutes. If you finish, okay, good. If you can't open it, let me know. But I know you can open it. I've sent it to other people, or you send me your email. Okay, I think I have your Gmail. Let me also share in your. I think I have your Gmail. Sent to me by. Okay, it's been shared. So carry on. So 20 minutes.
Hello, sir. Hello, I can hear you, sir.
Okay, I'm afraid 20 minutes is up. Am I sure? Yeah. Not quite up to 20 minutes. So can I get some result from us? Hello, who has finished?